Hey guys, what's up? So we're back in chapter 1.5 review questions. We're almost done like most of the questions here. I'm not going to do all the questions, but I'm going to do one more question which I think is a little bit more tricky because the wording might be a little bit confusing. So let's get on to it. So question number 6, a rock is thrown at an angle of 65 degrees above the horizontal at 16 meters per second up a hill that makes an angle of 30 degrees with the horizontal. How far up the hill will the rock go before hitting the ground? So this question is a little bit tricky, so I'm going to go ahead and make a diagram for it. So you can just ignore this part for now, I'll explain it after. So you know that the angle that you're throwing the ball at or the object is 65 degrees above the horizontal. So let's say you're in this position A and the angle you're throwing it at 65 degrees. So you throw it and that the hill is also on an angle, but this angle is 30 degrees. So this line represents the hill, this line represents your velocity, your object that you're throwing. But then when you throw the object, the gravitational acceleration actually tries to bring it back down, which is why you get like an arc shape. Now the question is asking you where or how far does the object land on the hill. So what you're given is you're given this velocity that you're thrown at, you're given the angle, and you're given the angle of the hill. So to find the distance that the ball lands on the slope or the hill, what you're going to have to do is you're going to have to find the time it takes to land on the hill. So to do that, first I'd recommend that you find the x component and y component of this velocity just to make the next few calculations easier. So I've already gone ahead and done that. 16 cos 65 gives me the x component, 16 sine 65 gives me the y component of this velocity. We know that the gravitational acceleration in the y direction is going to be negative 9.8 meters per second squared up, which is 9.8 meters per second squared down. So we're given all of that. So if I want to find the point where it lands on the slope or the hill, well, let's see. If I know the x component velocity and the y component velocity, I could probably find the displacement in the x component and the displacement in the y component. Since I want to find the distance on the slope, I could just find the x component distance and the y component distance and use that somehow to find the distance that the ball has traveled on the slope from my point. So I'm going to go ahead and find the y component displacement. So displacement y is VIY times time plus half acceleration times time squared. We already have VIY, but we don't have time. And since we want to find the time it takes to land here, it makes sense to use this. So dy equals 16 sine 65 times time minus 4.9 times time squared. 9.8 times half gives us 4.9. And since it's negative 9.8, this sign becomes negative. So now that we have an equation for the y component displacement, we can go ahead and find an equation for the x component displacement, which is just going to be velocity in the x direction times time, which is basically 16 cos 65 times time. So now that we have an equation for the y component displacement and an equation for the x component displacement, so the ball lands on some point on the slope. So some point on the slope. So we have the y component displacement and the x component displacement of this ball landing on here. And we know that the slope is, or the hill is on a 30-degree angle. So since we have the y component and the x component, and we have the angle, we know that the tangent ratio is opposite over adjacent. So what we could do is we could do tan 30 equals opposite, which is the displacement in the y direction, over adjacent, which is displacement in the x direction. And that's basically what I've gone ahead and done in the next step. So tan 30 equals displacement in the y direction, which is this equation, over displacement in the x direction, which is this equation. So I evaluated 16 cos 65 and I ended up getting 6.76 times time. I moved 6.76 times time on that side, so I got 6.76 times time times tan 30 equals 14.5 time minus 4.9 time squared. So if I do 6.76 times tan 30, I end up getting 3.903. So 3.903 time equals 14.5 time minus 4.9 time squared. And this kind of looks like a quadratic equation, which is good. We could just factor out the t-value to get our time. So I'm going to move the 3.903 time to the other side. So this becomes negative now. So negative 4.9 time squared plus 14.5 time minus 3.903 time. I just add the 14.5 and this, since they both have time, since they both have like variables, like terms, I can add them together. And I end up getting negative 4.9 time squared plus 10.596 time. So now what do I do from here? Well, since I wanted to find the time it takes to land on a certain position or a certain distance on here, since I wanted to find that time, and I'm left with this equation, I could just factor out time, because they both have time as a common variable, right? Since here they have time and here they also have time. So I could factor out time, and I can also factor out 4.9, negative 4.9. So that's what I've gone ahead and did in the next step. So negative 4.9 time times time minus 2.162. I factored it out and I got this. So if I set this part to 0, I get time equals 0. And if I set this part to 0, I get time equals 2.162 seconds. So in 2.162 seconds, that's how long it takes for the ball to hit the point on the slope or the hill. So that's how much time it takes to land on the hill. So now that I have this time, I can find the displacement in the x direction, since I already had the formula from before, VIX times time. VIX is basically 16 cos 65 times 2.162 gives me 14.622 meters in the x direction. Now I find the displacement in the y direction. I use the previous formula that I had here. 16 sine 65 times time minus 4.9 times squared. And I end up getting 9 times. I end up getting 8.447 meters in the y direction. So I've already gone ahead and drawn a diagram. This is dx, which is what we just got here, and this is dy, and we want to find out how far it's gone up the hill. So we can just use the Pythagorean Theorem. So d equals root 14.622 squared plus 8.447 squared plus 14.622 squared, and then take the square root of that, and that gives us 16.88 meters, which is approximately 17 meters. 17 meters from your starting position. So the ball basically lands 17 meters from your starting position, or you could say 17 meters 30 degrees above the horizontal from your position. So yeah, that's how far it's traveled, or distance is traveled from you up the ramp. So yeah, hopefully this video helped you out in this problem. I know it's a little bit tricky, but it doesn't look that hard after you've gone through the steps. And yeah, hopefully this has helped you out. And if you have any questions, feel free to comment below, and I'll see you guys in the next video.